Okay, so this is going to be problem number 80 from section 3.2, I believe. I assigned you this problem kind of knowing that you were going to maybe have questions with it, and because it's dealing with something that we quite frankly haven't talked about, so and it's not a bad thing. It just is. So let's look at this. You got this graph of this sort of piecewise function here. It's what we call piecewise linear. It's actually three different linear functions put together. Back in Algebra 2 or pre-calculus, maybe you would have had to write an equation for this piecewise function. So you would have probably written something that looked like this. And then you would have had different conditions for x. Like the first branch would be x between -3 and 0. And the next branch would be between x is between 0 and 2. And then the next branch would be x is greater than 2. Oh, actually, it's like between 2 and 4. So it would be three different branches. You would have to find the equations of those three lines to do that. But that's not what we're interested in doing right now. What we're interested in doing is finding these various derivatives here. And if you notice the way the directions read, if you read them, which you should always read the directions said, find the derivative if it exists. Okay? And we haven't really had an issue where the derivative didn't exist before. So this was kind of going to be our entry point into this. So let's just jump in here. It says f prime of -5. So if I'm looking at this graph here, what's the derivative at -1/2? So -1/2 is here. Well, this function is just linear between there and there. And the derivative of a linear function, if you haven't made this connection yet, the derivative of a linear function is just the slope of that linear function. I just thought of something. I want to check the microphone. I'm going to pause real quick. Well, hopefully I have the right microphone turned on and you guys can hear this okay. If not, I'm going to be really upset. The derivative of a linear function is just the slope of that linear function. So if I look at this, f prime of 0.5, well, what's the slope here at 0.5? Well, the slope's constant all through there. It looks like the slope of that line is -1. Okay? But now at x equals 0 is where things go south. Things become problematic at x equals 0 because what's going on at x equals 0? If we're looking right here at x equals 0, this function takes an abrupt change. Okay? It's going nice straight up and then straight down. There's an abrupt change, right? So at x equals 0, if I were to think about what's a tangent line look like at x equals 0? Well, a tangent line could be maybe right there. That's tangent at x equals 0, but so's that. And wait, so's that. Okay, there are lots of tangent lines at x equals 0. There's no gradual change as we go over the hill like a roller coaster. There's no gradual change. It's just straight up, straight down. Okay? So because of that, we can't say that there's a defined slope at x equals 0, right? So here's where we say the derivative does not exist. Okay? We actually call this point right here a cusp. Okay? A cusp. A cusp, the technical definition of a cusp, is a point where the function is continuous but not differentiable. And I'll explain what that means as soon as we're finished with this example. But a cusp is basically a sharp point. So now if I look at f prime of 1, so f prime of 1 right there, oh, we're nice and linear right there, no abrupt changes. F prime of 1 looks like -1. Oh, I just noticed something. I did the same thing yesterday when I was talking to somebody about this. This slope right here at f prime of -0.5, I don't know what crack I was on here. That's a positive slope, so this is a positive 1, not a -1. This one is -1. Yeah, sorry about that. Still early in the morning. Okay, so f prime of 1 is -1. Now we're going to go to f prime of 2. Same thing happens. Check it out. Woo. There's a tangent line. There's a tangent line. There's a tangent line. There's an infinite number of tangent lines there. There's no gradual change on there. So this is another what we call cusp. Woo-hoo. We know that word now. Okay? So the derivative does not exist there. Okay? F prime of 3, now that's 3 is right in here. Now we're back to a normal line. So we'd have to calculate the slope of that line. It looks like this line goes up 4 and over 2, so the slope is 4 over 2, which I guess you folks like to call 2. Okay? So those are the solutions to that problem. Now what I'm going to do is I'm going to pause the video, I'm going to erase the board, and I'm going to kind of tie this information together to kind of give you a more formal definition of what a cusp is and what differentiability really means. So let's do that. Okay, I lied. I said I was going to erase the board, but I didn't because I decided I want to use this graph to bring this together. So I'm going to now take this graph, and I'm over here. I'm going to take this graph right here, and I'm going to sketch the derivative of this function. Okay? I'm going to sketch the derivative of this function. I'm going to do it in a different color. Let's do it in orange. All right, so here we go. So between -3 and 0, it looks to me like the derivative is just a constant 1, right? So here's -3, and here's 0. So the derivative is just, I'm going to put, here's x equals 0, here's 1. I'm going to say the derivative is just a constant 1. Okay? And then between 0 and 2, the derivative is a constant -1. And then between 2 and 4, the derivative is a constant 2. Okay? So that's what the derivative looks like. Now, if you think about this for a second, these two values, there is no derivative at x equals 0 and at x equals 2. We just said that over in a second ago. So there should be technically open circles here indicating that the derivative does not exist at those points. Okay? And on the very, very ends, I don't know what's happening on the other side of -3 and -4, so I'm going to leave those open as well. Okay? So this is the derivative of this function right here. And if you notice, the derivative function is not continuous at x equals 0 and at x equals 2. Oh, forgot to open hole there. Okay? The derivative is not continuous at x equals 0 and at x equals 2. That's what it means to be not differentiable. Differentiable. Not differentiable. I don't know why I'm writing in all caps. Not differentiable. Okay? The derivative is not continuous. Okay? That's what happens when we have a cusp. The derivative is not continuous. Now, a cusp is a point on a function where the function is continuous. Like this function, I mean, this is a continuous function here, right? However, the derivative is not. Because at this point and at this point, the derivative is over here, and so the derivative is not continuous at 0 and at 2. That's what we call a cusp. The function is continuous, but the derivative is not. Okay? Now, there's a big rule that I'm going to kind of explain to you here after I erase the board that kind of ties these ideas together of continuity and differentiability. So I'm going to pause. Okay, so I've now erased the board. Now we're going to kind of tie these ideas together. And this big rule, this theorem, if you will, you know, whatever, big rule, theorem, whatever you want to call it, is that if a function is differentiable, if a function is differentiable, Now, what does it mean for a function to be differentiable? It means that the derivative is continuous. If a function's derivative is continuous, then the function is continuous. Okay? So if you've got a differentiable function, you have to be a continuous function. Now, this argument does not go the other direction. Okay? It does not say if you have a continuous function, then you have a differentiable function. And the counterexample of that is the cusp. Okay? This does not say if continuous, then differentiable. It does not say that. Because the example of that, the counterexample of that, is the cusp. Okay? A cusp is an example of a point where a function is continuous, but its derivative is not. So that's the big rule. Okay? And honestly, the way we will probably think about this rule more often is in the form of its contrapositive. Okay? Because another equivalent statement to saying this right here, okay, is what we call the contrapositive. I'll write that big word down. Contrapositive. Contrapositive. Okay? I'm not sure if you're familiar with what the contrapositive of a statement is, but a statement and its contrapositive are logically equivalent statements. So, for example, if I say, if it is raining, then there are clouds in the sky. Okay? If we say, okay, yeah, we agree with that. If it's raining, then there are clouds in the sky. There's an equivalent way of saying that same statement with a negative condition. And an equivalent way of saying that same statement is, if it is no clouds in the sky, then it is not raining. So if no clouds in the sky, not raining, is equivalent to saying, if it's raining, then there are clouds in the sky. Okay? So the contrapositive of our statement that's equivalent, that's going to be very powerful for us, particularly when matching up derivative graphs, is, so let's go back to the statement. If a function is differentiable, then it's continuous. So you negate the conclusion, so you say, if a function, so I say or here, these two are equivalent. If a function is not continuous, you continuous, then it is not differentiable. Okay? If a function is not continuous, then it's not differentiable. Okay? These two statements are equivalent. And how that's helpful is if you see a function, say, that has a vertical asymptote, like, a lot of those graphs that you guys were matching up, let's say that's what your vertical, your function, and you were trying to find the derivative of that function. This function's not continuous right here at that vertical asymptote. Then guess what? Its derivative's not going to be continuous there either. Okay? That's the way that we can use this. So if a function has an asymptote at a certain place, then the derivative is going to have an asymptote at a certain place. Okay? So what I'm going to do is I'm going to pause this, and I'm going to do an example of this idea. And then, yeah, that's it. So hold on. Okay, so here I've got a piecewise function on the board here. And the question for you and the question for us is this function continuous and differentiable at the point where it switches? Or is it just continuous? What's the deal? What's going on with this function at x equals -5? Because that's where the function changes. This is a piecewise function. Now, you could graph this and kind of see, oh, is there going to be a sharp point there? Is there a cusp there? You can get a visual of it. We're just going to jump in and kind of answer the question algebraically. So the first thing I'm going to do is determine whether or not this function is continuous at x equals -5. And the easy way to do that is just first to show that if we approach -5 from the left and we approach -5 from the right, that they're going to the same thing. So I'm going to calculate these two limits from the left and the right and see if they're going to the same thing. And then we obviously know that f of 5 is going to be by I'm sorry, not 5, -5. F of -5 is going to be what I plug in when I get to this bottom branch here. Okay, but these are two functions here that are easy to calculate these limits. So I'm going to say, all right, the limit as x goes to -5 from the left. I'm going to use which one of these is the left of -5. It's going to be this rule right here. So that's x squared minus 6x plus 8. And then the question is does this equal the limit as x goes to -5 on the right side, which is -16x minus 7. Okay? So what happens here as x goes to -5? Okay? What are we getting here? So we're going to have -16 times -5 minus 7. If we want to do that on a calculator, $73. I'm just lazy. I didn't want to do that arithmetic in my head. And does that equal 73 on that side? So do I get 73 when I do this arithmetic? So that's going to be I sure do. Because the original function was 18, not 8. When I first did that, I got 63, and I was like, wait, I know this works because I did it earlier. Yeah, that's 18, not 8. So, yeah. So on both sides of -5, this function's going to 73. So, here's -5 over here. If I were thinking graphically, this function, whatever it's doing, up here at 73, on the left side, it's approaching 73. And on the right side, it's approaching 73, okay? So now we're going to determine, so we know it's continuous, okay? Because these two limits are the same, and they both equal f of -5. Now we're going to determine, is it differentiable at x equals -5? Is the derivative continuous? So in order to answer that question, I'm going to erase this a little bit, give myself some more room. In order to answer that question, I'm going to determine, is the derivative continuous? Okay? So first I've got to find the derivative. Okay? I got to find the derivative here. Now, in this particular problem, I'm going to kind of cheat. I'm not going to find the derivative the long way, like using the limit definition, because the next video that you're going to see is I'm going to teach you the shortcuts. So I'm just going to use the shortcut here. I'm not going to go through the limit as h goes to 0 of f of x plus h minus f of x all over h. I'm just going to calculate the derivative right here. So the derivative of this guy is going to be 2x minus 6. And that's going to be x less than -5. And the derivative of this guy, and quite frankly, you shouldn't have to go through the limit definition for this one because this is linear right here. And you should be able to tell me the derivative of a linear function just by looking at it. It's the slope, right? So -16. For x is greater than or equal to -5. Okay, so there's our derivative function right there. Okay? Is that derivative continuous? So let's do the same thing that we just did over here. Let's look at what the derivative is approaching on the left side of 5 and on the right side of 5. So I keep saying 5. I mean -5. I'm just so excited. I can't control myself. So are these guys equal? From the left and the right. Well, the right side's easy, right? What's the limit? What's the derivative approaching on the right side of -5? Like right here. It's always -16. Okay. What's the derivative approaching on the left side of 5? Well, maybe we got to do some algebra. So we say limit as x goes to -5 of 2x minus 6, and we do some arithmetic there. Again, we were still wondering, are these two equal? And look at that. They are. Okay? So, the answer to this question, is f prime continuous at this point? Yes. Yes, it is. Okay? The derivative is continuous. So we've got the derivative continuous, we've got the function continuous, so this function is continuous and differentiable. If we were to graph it, okay, and maybe I challenge you to graph it on your calculator or on Desmos, you'll see that there's a smooth transition that happens between here and here. Okay? It's just a smooth curve. In fact, the word smooth in mathematics actually means differentiably differentiable. A smooth curve is one whose derivative is continuous. And if you keep taking the derivative in the second derivative, the third derivative, fourth, etc., that's what a smooth curve is. So smooth basically means we're differentiable. Okay? So that's what causes smoothness. Yeah, so tell your friends you have a new definition of smooth. So that's the end of this. I'm going to give you some problems to play with this idea in Delta Math. Don't forget you have a quiz that's due, but I probably already talked about that in class.